Hi guys, welcome to the lecture series of partial differential equations. So we are discussing first order partial differential equations. In our previous lessons, we discussed about the integral curves, formation of PDEs, and then linear, semi-linear, quasi-linear, and non-linear PDEs. So we also discussed some initial value problems associated to the Cauchy characteristic method. So today we will discuss nonlinear PDEs, and to find the general solution of nonlinear PDEs using Jacobbi's method. So let's talk about Jacobbi's method. So first of all, we'll see that how this method works and how to start solving a problem using this particular method. So let's say that if we are given a function that is a function of x, y, z, p, and q that is equals to 0. So we are given a nonlinear partial differential equation, a function of this type. So what we have to do is, first of all, we have to assume that the partial derivative with respect to x, that is p, is equals to negative ux over uz, and the partial with respect to y is equals to negative uy divided by uz. So the problem will be transformed from pq to ux and uz. So we will be having a function of the form f of x, y, z, ux, uy, uz, and a, where this a represents the constant. So the PDE from this form will be transformed by using this transformation into this form. So now after that, we have to form an auxiliary equation. So the auxiliary equation for Jacobbi's method is given as dx divided by fux, that is equals to dy divided by f of uy, that is equals to dz over f of uz, that is equals to dux divided by negative fx, that is equals to duy divided by negative fy, that is equals to duz divided by negative fz. So the first thing is that if a problem is given, so we will transform the problem from pq to ux, uy, uz, and then we will find these derivatives for their respective functions. So let's take a problem and start solving it using the Jacobbi's method. Let's say that we are given with a problem z square is equals to pqxy. So now we can see that this problem, this is a function. Basically, we can write this as f is equals to z squared minus pq xy. All right, so first of all, what we have to do is we have to assume that p is equals to negative ux over uz, and q is equals to negative uy over uz. Now we'll plug these values in the original equation, so the function will be transformed in this manner: minus ux over uz times negative uy over uz times xy, negative sign here. So now we can see that the function is transformed from pq to uxy, ux, uy, and uz. So now what we have to do is we will just make some simplifications. So we can write this as z squared minus ux uy times xy over uz squared is equals to 0. This is actually equals to 0. So now we can write it as u z squared z squared minus ux uy xy is equals to 0. So now the next step is to find the derivatives, respective derivatives with the respect to their functions. So let's find fux. So we have to differentiate this with respect to ux. So what will we get is negative uy times xy. Then for fuy, we will differentiate this function partially with respect to uy. So we will get negative ux times xy. Then we will differentiate with respect to uz. So we will get 2z squared uz, and then fx. So we will get negative ux uy times y, then fy. So we will get negative ux uy times x, and then finally fz, that will be equals to 2z times uz squared. Now we'll plug these values in the auxiliary equation. So what we'll get is dx over fux, that is negative uy xy is equals to dy over fuy, that is negative ux times xy, then dz or fuz, that is 2z squared uz, and then dux divided by negative fx. So fx is negative ux uyy, so it will be positive ux uy times y. then duy divided by f of y, so it will be ux uy x. Then finally duz divided by f of z, that is 2z uz square with negative sign. Right. So now we construct the auxiliary equation. So now we have to solve using the pairs of these differential equations. So now we are very much familiar with these solving the pairs, because from the very beginning and integral curves, and then after that for Cauchy's characteristic we use the pair. So now we'll take this pair dx with this pair dux. So dx divided by uy times xy is equals to dux divided by ux uy times y. So this uy with uy and y with y will cancel out. We will only left with dx over negative x, that is equals to dux over ux. So now this equation is a separable equation and this is solvable, so we will integrate both sides. Here we will get negative ln x, here we will get ln ux plus ln c, or we can just write ln a. So we will use b and c in the latter parts, so we just write ln a. And now we can write this equation as ln ux plus ln x is equals to ln a. We are not very much interested in the sign of this constant function, because we don't care if it's negative or positive, because it's an arbitrary constant. So it's just like we shift this equation to the right, ln x to the right hand side and this ln a to the left hand side, but we are not interested in the sign of this constant function, because this is an arbitrary constant, right? So now we can write x times ux is equals to a, because here we use the property of log, that is log x times ux will be equals to ln a, and when we take base e to the both sides, so we will left with x ux is equals to a. Now we will use the second pair. So what is the second pair? Let's see. So second pair is this dy over negative ux xy and duy over ux uy x. So we can see that this ux with ux will cancel out, this x with this x will cancel out. So we can write that dy over negative ux xy, dy over negative ux xy is equals to duy over ux uy times x. So this ux and ux will cancel out, this x and x will cancel out. We will only left with dy over negative y, which is equals to duy over uy. So this is also a separable equation, so we can integrate this equation. Similarly, what we will get is ln y is equals to ln uy plus ln b, and again we are not interested in the sign of this constant function, so we shift it to the left hand side. It will be ln uy plus ln y. Again we can write it as the property of log, that is y times uy with the function of log. So we'll take the base e to just cancel this log, so we're left with This implies that uy is equals to b over y. So you see now we are approaching to the solution. We got ux, we got uy, now we'll work for uz. So we'll take the equation of dz and duz. So dz divided by 2z square uz, 2z squared uz is equals to duz divided by duz divided by negative 2z uz square. So this z will cancel out with this z, this uz will cancel out with this uz, so we will only left with dz divided by 2z is equals to duz divided by negative 2. Instead, in fact, we have to cancel this also, so we can only write z and here negative uz. So this is also a separable equation, so we'll solve it. We'll get ln uz plus ln c. So again, we can write this. I'm writing it directly, so we can write it as zuz. So this implies that uz is equals to c over z. Right, so we found all ux, uy, and uz. So the next step is so now we have to take this form du is equals to ux dx plus uy dy plus uz dz. So we'll write ux. What's ux? So ux is equals to, sorry, I forgot to write here. This implies that ux is equals to a over x. So I can write a over x in place of ux and b over y in place of uy and c over z in place of uz. So I will write a over x dx plus b over y dy plus c over z dz. So now all these are solvable for you, so we can write it as a log x plus b log y plus c log z plus d. Or in fact, we should, okay, it's fine if we don't write as ln d, it's fine. So u will be equals to ln x power a plus ln y power b plus ln z power c plus d. I use the laws of logarithm to shift these coefficients to the power of x. So now I will use another property of log, that is log x plus log y plus log z is equals to log x y z. So I can write it as a multiple of these functions. Right? So we can just stop here. It's the final solution, or we can just say that this u is equals to d. We can take that also, so we left with 0 is equals to ln x a y b z c, and when we take the take e to the power log to cancel this. So e to the power 0 is 1. So this will be x power a, y power b, z power c will be equals to 1. Or you can write it explicitly for z like this. This implies that z power c is equals to 1 over x power a, y power b. So if we want to simplify, it will be uh, square root of c times c multiplied by yb. So this is the final answer. And this is the method for Jacobbi's to solve nonlinear partial differential equations. Very important method, and it's used to solve PDEs of nonlinear PDEs. You can solve using Charpit's method, Monge's method, and this Jacobbi method. So just you need to focus on the steps that we followed throughout the problem. So you will get familiar with the procedure of this method. So thank you for watching video.